Hello students, and welcome to section 5.4 on sampling distributions and the central limit theorem. So in this video we're going to talk about sampling distributions, and we will discuss the main points of the central limit theorem. So let's quickly review some definitions. A sampling distribution is the probability distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a population. If the sample statistic is the sample mean, then the distribution is a sampling distribution of the sample means, and we'll talk more about that later. So every sample statistic, whether it's the sample mean or some other sample statistic, has a sampling distribution. So let's discuss these ideas a little further. So when we talk about random variables that are quantitative, so remember a variable is quantitative if it measures something about an object or individual, right? Or if it counts something about an object or individual, so such as a person's height or the number of pets they own, right? We want to calculate probabilities associated with those random variables. So in order to calculate probabilities, we need to know the probability distribution of that random variable. So we've discussed discrete probability distributions, such as the binomial distribution and the normal distribution earlier in chapter 5. So under certain conditions, quantitative random variables can be modeled with the binomial distribution, as we discussed in chapter 4, or they can be modeled with the normal distribution as described earlier in this chapter. In some cases, another probability distribution is used to model a random variable. So in any case, every random variable can be described by a probability distribution. So when we refer to the distribution of a random variable, we must describe the distribution using the following characteristics. So we need to describe the distribution with its shape, center, and spread. So by shape, we mean how the probability distribution looks when it is graphed. In other words, is the graph of the probability distribution bell-shaped and symmetric like the normal distribution, or does it have some other shape? So by center, right, we ask what is the mean of the random variable. So remember, another word for mean is average. And then by spread, we ask what is the standard deviation of the random variable. So the spread of a distribution determines how spread out or dispersed the values of the random variable are. So by knowing the shape, center, and spread of a probability distribution, we can use that information to help us answer questions about the random variable it is modeling. So in this section, we will focus on the sampling distribution of the sample mean. And remember, the sample mean is represented with the symbol x bar. So the question is, why would we care about the sampling distribution of the sampling mean? So remember, the sample mean is a random variable. So I'm going to use this diagram to describe why the sample mean is random. So in order to have a sample mean, you have to have a sample. So for example, let's pretend that this is the population of the state. So you might recognize the outline of the state as the state of Massachusetts. So for example, this could be any state. All right, and let's say we measure the blood pressure of each person in the population. So if that were possible, right, we could calculate the mean of the population, and let's just say that the mean blood pressure of the population is 78 millimeters of mercury. So normally we won't have that information, right? We won't know the population mean, but in any case, let's pretend that we do. All right, and let's say that we take random samples from the population. So for each random sample, we can calculate the mean blood pressure, but before we do that, we take blood pressure readings for each individual in our sample. And once we have the individual blood pressure readings of each person in the sample, we can calculate the mean of our sample, called the sample mean. So for example, one sample might have a mean of 75. The mean blood pressure might be 75. At another sample, the mean blood pressure might be 67. And then yet another sample, the mean might be 71.3. So you can see that if we take a random sample from the population and calculate the mean of each sample, we can see that the mean of each sample is going to vary. So meaning the sample mean is random, right? We don't know what the sample mean is in advance. Okay, so the sample mean is a random variable. So each time we collect a different sample from the population, the mean of each sample will be different. Okay, you can see more about this on page 261. Okay, so here we have a box that represents the population, and each circle is a random sample of the same size. Okay, so for example, in sample 1, the sample mean might be x1 bar. In sample 2, the sample mean might be x2 bar, and so on and so forth. Okay, so there are no specific numbers that we're attaching to these sample means, but this is just to show you that each sample will give you a different sample mean. Okay, just like this diagram is showing you. So the sample mean will be different even if the size of each sample is the same. Okay, so as you can see, the sample mean is a random variable. Okay, so if we know that something is a random variable, that means it's possible to describe it with a probability distribution. And then once we have a probability distribution, we can describe its shape, center, and spread. So what does this have to do with the central limit theorem? So the central limit theorem, or CLT for short, will tell us when we can use the normal probability distribution to model the sample mean x bar. So the central limit theorem is summarized on page 263. Okay, so let's take a look at what the central limit theorem says. Okay, so if random samples of size n, right, where n is greater than or equal to 30, are drawn from any population with a mean mu and standard deviation sigma, then the sampling distribution of the sample means approximates a normal distribution. So the greater the sample size, the better the approximation. Yes, that's the first point. And the second point says, if random samples of size n are drawn from a population that is normally distributed, then the sampling distribution of the sample means is also normally distributed for any sample size n. And then it says, in either case, the sampling distribution of sample means has a mean that's equal to the population mean, and then the sampling distribution of the sample means has a variance equal to 1 over n times the variance of the population, and a standard deviation equal to the population standard deviation divided by the square root of the sample size. Okay, so those are the main points of the central limit theorem. Okay, so before we end the video, let's go ahead and paraphrase what the central limit theorem is saying. Okay, so here are the main points. So for any population, the sample mean can be approximated by the normal distribution, provided the sample size is large enough. So usually the sample size n must be at least 30. So in other words, n is greater than or equal to 30, okay, where n represents our sample size. The larger the sample size, the better the approximation will be. Okay, so point 2 of the central limit theorem says that if the population is known to be normally distributed, then the sample mean can be approximated by the normal distribution for any sample size, even if the sample size is less than 30. So notice that the first 2 points of the central limit theorem are helping us describe the shape of the probability distribution for the sample mean. Okay, so in other words, the probability distribution for the sample mean is called the sampling distribution of the sample mean. Okay, so point 1 tells us that for any population, even if it's not normally distributed, our sample size has to be large enough. Okay, so the minimum size is usually 30. So 30 or more would be a good sample size. Okay, if the population is known to be normally distributed, okay, then any sample size is sufficient, and the sample mean will be normally distributed. Okay, so the first 2 points describe the shape of the probability distribution of the sample mean. Okay, so the third point says, furthermore, the mean of the sample mean is equal to the population mean. So this is the symbol we use for the population mean. So in other words, the mean of the sample mean, which is given by this symbol here, so mu x bar, is equal to the population mean. Okay, so that describes the center of our probability distribution. Lastly, the standard deviation of the sample mean is given by this formula here. So this is the symbol that represents the standard deviation of the sample mean, so sigma x bar. Okay, and this is equal to the standard deviation of the population divided by the square root of the sample size. Okay, so that describes the spread of the probability distribution of the sample.